Good day to you. This is Anagalactic bringing you another science presentation to follow up on yesterday's discussion of linear space. Linear space, of course, is the basis of all mathematics. We use a linear number system. Linear geometry. You do need to know what linear geometry so that you can identify the lacuna in the system. Lacuna just means a hole. Linear zero is the center of the system. It's the center of the linear system. No matter how many lines you draw, just one has zero at the center. That's called the Archimedean principle. That can be proved. I've proved it. The zero is at the center, essentially because the two infinities are hitting, they're hitting one infinity. So when you draw, it's a diameter of a sphere with two infinite endpoints. Well, that balances it, even though it's on an abstraction. They're equivalent infinities. So zero is the midpoint of plus and minus linear infinity. That's geometric. That doesn't really have anything to do with numbers. It means that you have a center of reference. That's called the reference frame, by the way. A very important principle, which is, I've never seen it taught correctly. What the hell is a reference frame? You can't understand relativity until you understand that it's all about reference frame. Well, what does that mean? You picture a frame? What, with a photograph in it? A 4D photograph in a frame? Kind of. Well, that frame has to have a center, or you can't measure anything. If you've seen a space-time diagram, which is a 2D projection of a 3D projection of a 4D system. We can't see a 4D system because it goes beyond volume space. So the fourth axis in the Einstein field equation is imaginary. Well, it turns out that's extremely powerful to get that imaginary fourth axis. So that's the end of the linear system in the positive sense. That's as far as it can go. That's been proved. 4D is as high as you can carry linear systematic space, which begins with 2D, as you know, which is on an orthogonality, which is the basis of mathematical geometry, is the right angle for that reason, because the two lines have a relationship. And you can see that it's got a symmetry. If you add a third axis to make volume space, which we call 3D, it's now completely imbalanced. You have a three-line system. So now you have, how many orthogonalities are in that system? When you have two lines, you could say there's one orthogonality. Although you could also say there are four, right? Four orthogonal. Yeah, plus plus, minus minus, minus plus, and plus minus. Those are four orthogonal angles. Well, that's the basis of mathematical geometry, is that right angle. That's where we get the right angle law, always mispronounced as well, now you have to look up to get his well, it's the right angle law is what it is. So now you add the third axis and you have volume space. How many orthogonalities do you have now? Well, you could say 3. But I think if you counted, you would find more than 3. And you can add some Pascal's triangle. You can get the number of orthogonalities in a 3D system. But it has nothing to do with reality. Nothing whatsoever to do with reality, except that's not quite true, or it wouldn't work at all. Oh, it does work. We use calculus in order to get approximations on spheric numbers. That's what I discovered in 2022. So let's make sure we cut through the gobbledygook, because even when I say it, even though I'm the one who discovered this, it still sounds like gobbledygook. Because what are you talking about, Sam? That's actually my initials. My real name is Scott, but I'm known as Sam around town here. because I'm from the campfire, and somehow my name changed after the campfire destroyed my life's work and home. I'm riding. I'm still riding. No, not a problem. You just start over. You know, that's actually good sometimes. You just clean house and start over. So it did me some good. I hope it does you some good, or I'm just as useless as Eric Weinstein. Because I don't think I'm as entertaining as these guys. I'm not an entertainer. Although I would like to be. You know, you lead two lives, right? You have to maintain yourself as a human. You're not a scientist. You're a human, okay? But if you're also a scientist, you have two sides. That's the way it is. So, why would we even be doing science? I say it's a religious quest. I don't know if most people look at it that way, but as you get older and wiser and learn and start dealing with reality in your own life and face some facts that are very difficult to face, you will come to realize why you're attracted to science. It's because you're blueprinted to get understanding. So it's very important to know the basis of your understanding, or you could just build a fairy tale kingdom and just pretend that you know relativity and quantum mechanics and just pretend, without it ever actually mattering. And that's actually somewhat of a fundamental philosophical paradox, is why are we doing science at all? There's never been a defined ultimate purpose to science. We don't know exactly why we're doing it. Empirically, we found out it's very beneficial to do science because we get technological advances. And that's taken the place of the definition of science, which is now technology. Well, that's pretty obvious, and you may realize that really leaves things incomplete, because technology is not the solution to anything except temporary survival. Is that all science is for, is to make us comfortable, more comfortable? Well, that may be good enough for most people. It's certainly good enough for me. I don't say that linear algebra is bad. I don't say that technology is bad or wrong, although it's used for evil, but what isn't? So linear algebra is fine. You understand, this is not to pull down any pillars. What it is to give you choices of orientation, because if you have a frame of reference, which you must have, then you have to use your frame of reference to get some kind of perspective on reality. Well, that's all very broad stroke. But if you begin with a linear system, you're going to run into a brick wall eventually. Well, we've hit it. We hit it in the 20th century. Everything in the universe looks like this. The center of the frame of reference is the center of a spherical frame of reference, and everything that we know in physics propagates spherically. Nothing is linear. There's a footnote. Galactic jets are linear. They go in two opposite directions. Those jets, superluminal jets, superluminal, just understand there's a footnote to that as well, because they're not going faster than light, but they look like they're going faster than light. There's a reason for that. So there is linearity in the universe. In fact, in many of my presentation series over the past 2 years, which is based in astronomy and ultimately cosmology, that we want understanding. That's what cosmology is. It's understanding astronomy. Well, now we know that in order to understand astronomy at the level we need quantum mechanics, because that explains light. So that's the reason for the madness over quantum mechanics, which is where our mathematics hit the brick wall. Now, in deep space science, the same thing happens. The formulation of the supermassive black hole is based on a sphere. The supermassive black hole is a sphere. But we measure it using linear geometry. Well, that's why there's a singularity. That's a mathematical error. So nobody really knows anything about the supermassive black hole except what can be directly deduced from the data. There's definitely a gravitational locus, but whether it's even an object or not, nobody is certain of that. Well, I have a significant point of view on that based on spherical geometry. So today, as the sun is rising for another 110-degree day, and I'm already sweating copiously, I'm sorry, I hope you can't see that, but the AC is off, so I have to speed this up. Well, that's a blessing, of course. I discovered the mathematical basis for spherical orientation, for a spherical frame of reference, which is what is missing in science all through it. We don't have a spherical frame of reference. Space-time is linear. It's a 4D system. That's automatically wrong. That can't possibly match reality because gravity is spherical. So how do you cope with that using the only mathematical system we'll ever have is linear mathematics? Well, that's only based on addition. The other three operators are meaningless. The line only has add. That's a proven fact. Well, you'd never hear that. That the line only has one operator, add. There are no other operators for linear space. Well, what about multiply? What about divide? What about the square function? What about the square root function? What about the calculus? The integral calculus and what are those? Do those just use add? No, they're different operators. Multiply and divide are the one we need to understand. That's a pair of operators. Just as add and subtract are a pair. You don't need subtract. It's only add. But when you get to multiply and divide, they're not inverse in the same geometric sense. Nobody has ever realized that, is that multiply and divide do not pertain to the line. Now, because we began with a hammer, everything looks like a nail. Or you could say we began with a nail, and now every tool we reach for has to look like a hammer. Well, there's actually another way to begin that's non-Euclidean. This is the true origin of non-Euclidean geometry. I'm the man who discovered non-Euclidean geometry. So I'm going to explain it to you for about the 20th time. I don't get tired of this. This is worth repeating. But it's so simple, I hope you find it so. Because if it's not simple, it's not true. It has to be simple to be true. That's a very deep and difficult concept to wrestle with, and you will for the rest of your scientific career. But at the end of the day, you will know that I'm right. So that's where I come from. If you don't like that, you can turn this off and go find a shyster. Like Eric Weinstein or Brian Keating. They will lie to you all day and make you feel good about it. If that's your bag, you're a free man, or whatever you are. Now, non-Euclidean geometry is simpler than Euclidean geometry. You may realize, and I have lectures on this if you'd like a little more in-depth foundation for linear spatial perception, you have to have a center to any mathematical system. Because it's a geometrical system, mathematics and geometry are virtually identical. So when you say linear space, you're talking about the Archimedean, which is the center of the system. The line has a center. If you want to use that center, which you must, you could begin the way Euclid did, who defined a point as a 0D object. That means by itself, the point is not even there. You're just imagining it. So you begin with imaginary space. Null, a 0. Now, to cut to the chase, is there any other way to begin? Yes, you could begin disregard Euclid. He said that a point is a 0D object. That makes perfect sense in linear space. It's actually tautological. If you want a number in order to get a line segment, one of the two numbers at the ends of the line, one of them has to be 0, or you can't get a metric for the space. It goes 1, 2, 3, 4, and then you get a distance. So that's the center of the linear system. It's 0, which I've covered in the past couple of lectures. 0 presents a huge problem in mathematics when you go to use division. And it's because the division multiplication operator does not work on the line. Now, nobody's ever noticed that. We're taught in school that it does work on the line, that mathematics teaches us that multiplication and division work on the line. What does it mean to work on the line? Starting with multiplication, you can do repeated additions. And that's how it's taught to us, that multiplication is repeated additions. That's true. And that's closed on the line. Closure means that when you begin with any two numbers on the line, that produces another number on the line. For instance, 0 to 3 yields 3. That's on the line. If you have 1 and you subtract 3, it's still on the line. It hits -2. So 1 plus -3 is -2. All of that makes sense, which seems to imply that multiplication is closed on the line. That's actually a strange superpositional illusion which you can prove to yourself instantly by showing the actual geometry of multiplication. It's linear, but it's linear systematic, because if you go 3 this way, everything's reversed on my screen. If you go 3 this way, and then you go 2 up, the area of the rectangle can be computed to 6, which is the same thing as going 3 twice, or going a jump of 2 3 times. So that we say from that multiplication is commutative. But what does that mean? Geometrically, what it means is you can start by going an x-axis distance of 2 and a y-axis distance of 3. And that actually is multiplication. It's a 2D operation. It's a 2D rectangular operation. If it's 2 this way and 2 this way, let me do that again. 2 this way. If it's 2 this way and 2 this way, that's still a rectangle, except it's a perfect rectangle. We call that a square. That's a squared number. See, I'm just centering this here a little bit. There we go. I don't want you to have to see that heater. All right, that's a little better, I hope. So multiplication already has two interpretations. It's either going linearly to stay on the line and closed, or you can realize what it really is, which is a 2D operation. Well, where does that leave division? That leaves division with a very serious problem, because it's not closed on the line. Division is not a closed operation, either on the line or in linear space. You can't even do division as a 2D operation. If you do it as the strict inverse of multiplication, you may be led to believe that it must be closed in the same way that multiplication is. That's not true. And it begins with a realization of what happens when you multiply by 0. Let's do that. So you have 3 times 0. So you begin the same way. You go 3 on the x-axis, but 0 on the y-axis. That means you have an area of 0. So we conventionalize that. There's still a distance on the line of 3. It's just you're not computing linearly, or you're not computing in 1D space anymore. It's not closed on the line. And multiplication by 0 proves that it's not really closed even for multiplication. Because if you go 7 times 0, that's, you still have the 7, but it's the same as the 3. Well, that's actually a contradiction. 3 times 0 cannot equal 7 times 0. We just say it does. And nobody ever explains that. It certainly wasn't explained to me in grade school. And I saw that, and I gave up on mathematics deep down inside me once we got to division. Because apparently I have a gift for mathematics, but it was throttled right then and there, and for the next close to 40 years, I only learned mathematics unwillingly because I knew that there was something wrong with it. Division does not work in mathematics. Division is not part of our mathematics. It's been imposed as if it were linear. Well, we know that division is a real operation. 2 over 1 reduces to 2, so there's some significance to division. Well, what is it? Well, if you begin the way we were taught, 3 times 0 equals 7 times 0. Because they both multiply to 0. Do they? Well, we accept that, but if you do, you run into an instant problem with division. Because division is the inverse of multiplication. But it's not the same kind of inverse as additive inverse. Additive inverse means if you go 3, sorry, when you go 3 and you go 3 the other way, that is 0. You go 3 this way and then 3 back, you arrive back at 0. So 3 plus negative 3 is 0. That's the Archimedean balance. So that makes sense. There's nothing wrong with addition on the line. It's miraculous. It's amazing. That's where we get mathematics from, is from addition. That's how we get distance. It's by using add on the line. All right. Now, where do multiplication and division fit in? That's a paired operator, just as addition and subtraction. But there's a different geometry to multiplication and division. And you can see it from the rectangle. That's a rectangle, not a line. Well, you just say, well, it's 2 lines. Yeah, but they're orthogonal. On a line, this is not orthogonality. It's polarity. It's 180 degrees. But multiplication is a 90-degree operator. 90 degrees. How does that affect division? Well, let's say you multiply your equation, just you plug in some numbers and you get 7 times 0. And then in the next step down, you take the inverse of that, not realizing that 0 might creep in there. Oh, it has to, because 0 is treated as a linear number. It is a linear number. It's a very special linear number. But when you use multiplication, you realize that there's something very strange about 0 in multiplication. Well, it becomes critical when you take the inverse of multiplication and you have a 0. If this step of your operation has a multiplication operation in it, and the next line down has a division operation, here's what can happen. You multiply 7 times 1, and in the next step down, you take the inverse of that. That works. Because 7 times 1 is 7, and then when you do 1 divided by 7, you get a number. A 1-component number. So that does seem to work. Well, what if it's 0? Now you take 7 times 0 in this step, which results in 0, And then you come to this step where it takes the inverse, and now it's 7 over 0. Or 0 over 7, but you lost the 7. Because once you get to 0, you're at the origin. That's not a new it doesn't have the same property as all other numbers. All other numbers besides 0 have a valence. They're either plus or minus. But 0 has no valence because it's null. It's not really there. All it is a placeholder for your measurement. Now all of that works for distance, and 0 works in the linear additive system. But when you divide by 0, you lose information. And that has been proved, so you must accept that. If you're unsure, look it up. I have previous presentations where I go into this in extraordinary detail to show the invalidity of 0 in the multiplicative division operation, which is a paired operation on orthogonality. Yes. So let's take a look at multiplication and division. Multiplication, we've already determined you can think of that as making a rectangle. What's happening is you're going in two directions at once. This simply does not happen on the line, except in repeated operations, where you can go this way and then come back. But if you're doing this and making a rectangle, you have to know how to get back. All right, that's pretty abstract. I hope I'm not muddling the issue. But all of this will clarify on an amazing insight, which is that if you begin in a non-Euclidean way by defining your point differently than you did with Euclid, Euclid began with his very first sentence in Elements. He began by defining a point as having no dimension, which means it's null. So it's very peculiar, this way to begin. That's the Euclidean system. It works marvelously for add. You need the 0 for add. So he did begin consistently, and the entire system of science is founded on that null frame of reference. That your frame of reference, your origin as we call it sometimes, is a very, very special number. Now, all is well, except you need to treat 0 specially if you're going to impose more mathematics, which we instantly do with multiplication and division. That's an error. And here's why. It's because multiplication and division do not apply to linear space. They're based on a different frame of reference. Multiplication and division do not allow the number 0. The number 0 is forbidden in multiplicative space because of the inverse operator called division. You cannot have a 0 in the denominator. That means you cannot have a 0 in the system. So the Euclidean formulation begins with a definition of a point that forbids the multiplicative space. So why do we use it? Because we've taught ourselves that we have to in order to use multiplication and division, which we want. Now, if you start correctly to get multiplication and division, you can derive addition without stumbling over 0. This is a magnificent insight. If you can follow this to the end with me, I'll make this as clear as possible, But this is a work in progress because nobody has ever seen this. Nobody in the history of mankind has ever seen this. Basic principle of mathematics, basic principle of arithmetic, that if you want division, you can't start with Euclidean space. So accept that and now follow the logic. You begin with a center and you don't say that it's null. Euclid had to do that. That was his first statement. The basis of the entire book of elements, which is expanded into the entire system of physics, is based on that zero being at the center of the system, your mathematical system. Well, if you begin a different way, without using add, you're just not starting that way. You're not starting with a line. Well, the way I've done this in my bootstrap sequence is to begin with a line for a very special reason, but it's not the Euclidean line. Because the center of the system, which is still right there at the center, when you draw that line, that is a Euclidean line, but without the definition of a point. You're only saying that it's a line, without starting the way, not Einstein, Euclid. Without starting the way Euclid did. There's a reason that he said that you must start with a definition of a point. It was because of his vision for what the line is for, which is linear spatial separation. That's add. So if you begin without numbers and start the way Euclid did, but without his definition of a point, you now have the original line, which we can now treat mathematically. So what happens is it has an Archimedean, it has a center, which can be proved from the fact that it goes to two equivalent infinities. This is not plus minus now. There's no concept of plus minus, because there is no need for an operator. We don't have an operator. We're just saying that it's a line. Now you know that that has the operator add on it. That's what Euclid proved. But we're not saying that. That's very important and subtle. It's one reason why nobody ever saw this. So let's follow it through so I can complete the sentence. This is very difficult in the inductive logical system to explain it, because all the work comes at the very first step. So I'm trying to make this easy on you. Disregard Euclidean addition. We're not excluding it. We're just not going to start that way. So the center, we're not even going to say it's a point, because that's prejudicial. It sounds like the Euclidean point, which is null. But you see, this system, we don't want zero. So you could say I have a prejudice, but this is the mathematical induction requires that you do go out on a limb for a moment. You go out on a limb, and then you prove that going out on the limb was the right thing to do. So that's what we're doing. But it's contrary to Euclid. Well, don't think of it. It's not contrary to Euclid. We're going to derive Euclidean space. But we have to start with natural space. And here is one of the most amazing insights that I think has ever occurred in the history of science. It just so happens that I saw it. I don't pat myself on the back, oh, I'm so brilliant. No, this was given to me. That's how a real scientist looks at things. You're being shown things. You're not inventing, you're being shown. All right, that's the true path of insight, is to realize that you're being shown things that are real. Let's make sure we can do that. We start with a line, it hits two infinities, their equivalent infinities is just plus plus. And those two balance on the center. That's called the Archimedean principle of balance of a system. You can prove that there's a center. So we now have a center and we have an edge. what I'm able to prove, I did this in 2022, that the two infinities exist on a spherical surface. What makes that peculiar is that it's an unbounded spherical surface because infinity has no mathematical definition. We're going to get one. So now we have two apples that we think we're reaching for. Let's hope we can prove it. We're going to get rid of 0, but we're going to get infinity. All right? So I hope that it excites you. You might think, well, he's a mad scientist. He's been out in the desert too long, and he looks happy, but, you know, I'm not buying it because he's nuts. That's how it should sound. Nuts. Because nobody's ever seen it. Well, am I just seeing a mirage? Let's find out. If you accept the hypothetical proposition that the line hits one infinity, which is an unbounded spherical edge, now you have a hypothetical proposition. You have two things now. You have a center and you have an edge. But you haven't defined either one. You have defined them in relation to each other. This is the center, and this is the edge. Can we relate them? Yes, we can. We can relate them mathematically. Okay, and that's what I'm going to show you now, and we're going to wrap this up. And the sun is rising, and it's getting hotter, so I'd better hurry. Interesting race against the sun here. This is true physics, you know, on Earth. This is how we do it. We have to race against the sun. Well, okay. So now we have an edge with no definition. Except what we said. It's the edge. Although it's strange. Because it's infinite and we don't even know what that means. But we kind of do. It's way out there. It's further out than we can measure. That's a good definition of the edge of a spherical, unbounded space. It has an imaginary edge. So let's hold that. That's actually a mathematical term, imaginary. So now we have three apples we're reaching for. We're going to get rid of 0. We're going to define infinity. And we're going to define what imaginarity actually is, physically. All right, so there's three apples to reach for. It's like a huge pot building up in Texas Hold'em, you know, and everyone's tense, like who's going to win. Well, this is a race against logic. Now, let's hope I can logically go on. I can. Here's how. You have an edge, and you have a center. Well, now you need numbers. Well, let's make some numbers. This is the real killer. As far as just imagining what to do next, I dared to study this, and I studied it for a very long time. You have a center. You have an edge. Can we give those numbers? Yes, we can. In a very interesting way. We call forward division. Because division is a very special operation. The way we portray it is with fractions, correct? Well, you can see that's a two-component number. Numerator and denominator. Let's use that as our basis. A two-component beginning. That's non-Euclidean. But what are these two numbers going to be? They're going to be linear numbers. And we're going to have to prove that. So there's a placeholder. We have to prove that the two numbers we put into the fraction to make a two-component division number, that would be in multiplicative space because multiplication is the inverse of division. I hope that makes sense. So we're going to say that this number at the edge, because it's not linear, this is a circular space. Circular and spherical are closely related. I use them interchangeably when presenting geometry this way. I've just learned it's easier. There is a direct relationship between the circle and the sphere. And I've proved the precise mathematical, which was known, but I simply brought it out, that the circle and the sphere are commensurable mathematically. They're precisely related. The same way the radius is precisely related to the circumference on an irrational number. Well, it's interesting that the circle in its relationship to the sphere is rational. So now we have 4 apples. We're developing a rational number system. That's the biggest apple of all, is to get a rational number system. So we have 4 big, huge, juicy apples. So you see, this can induce bias. Now you want to believe that you're going to get the answer. That's out. This has to be rigorous so that anyone can prove it to themselves. All right. We're going to say that this is a 2-component number space, and we're going to say that the numbers in the space are 2-component numbers exclusively, not to be reduced to a single component number. 2 over 1 is a 2-component number that we know we can reduce to a single component number. 2 over 1 is 2. Those are 2 different forms of 2. 1 is in relation to 1, but 2 by itself is not in relation to anything. If you're clever, you'll realize that 2 without being in fractional form is related to 0. 2 only has substance in relation to the center number. So now we have 5 apples. We're going to get a center number that not only is not 0, it's got to be rational. Well, that number turns out to be 1. 1 is the most peculiar number. And here's why. We're going to assign a number to the edge and another number to the center. The number that we assign to the edge, both of these are 2-component numbers. All right? So this is a 2-component number, a fraction. And this is a 2-component number, another fraction. We begin at the edge because we might. We could begin at the center, or we could begin at the edge. Actually, one of the difficulties in even imagining doing this is you really have to get both numbers at the same time. They have to be related. In linear space, +1 has a reflection of -1. +1 has a reflection, -1, that add to 0. If you go all the way to the edge, you have infinity and another infinity that add to 0. That's where we get polarity, plus/minus. That's called add and subtract. So that's consistent to balance the numbers in the system. In our system, we want the center number and the edge number to balance. But they're balancing in nonlinear space. That's 2-component space. So we have a vague match. This sounds like it's reasonable. Let's go on and assign a number to the edge. We're going to use lazy 8 with a very specific definition that it's spherical infinity. So that defines the edge, but it's imaginary. All right? So this is an imaginary number. It's infinity over 1. Okay, accept that. That's the hypothetical step. That has to be proved now, that does something good. What does it do? You have this number that's infinity over 1, and now we can use the principle of balance in multiplicative space. Is there such a thing? Yes. If you think of the 2-component numbers as being on a line, that is, you project it to a line just to see what it looks like, you can say that you have the center, and these numbers are numbers over 1 going this way. So that'd be 2 over 1, 3 over 1, 4 over 1, 5 over 1. The numbers going the other way are the reciprocal. 1 over 2, 1 over 4, 1 over 8. That makes sense, except this line is not jumping linearly. It's going doink, it's getting bigger and bigger with each jump. In the opposite direction, they're getting smaller and smaller with each jump. So that's nonlinear. That doesn't work on the line that we've ever been able to figure out. Although you can graph it. It's just that the metric going out is different from the metric going in. Are they so different? They're not linearly related, but they are geometrically related on the reciprocal. Because the two numbers that balance, 2 over 1 and 1 over 2, 4 over 1 and 1 over 4, every pair of numbers multiplies to 1. We're going to use that now in a very special way. So we have one number that's imaginary, and it's a 2-component number based on 1. Literally based on 1. It's like you have this line, which is division, and underneath the line, it's supported by 1. And on top, like the vase or vase, is your other number. In this case, it's lazy 8, which we've defined to be spherical infinity, and it's imaginary. So we have an imaginary number at the edge. Well, that sounds rather fanciful. If you invert it, it's 1 over the same number. We're going to say that that's the center. And that's our frame of reference, is the center. But it's not 0. It can't be 0 because it's not based on an Archimedean of 0. We don't have an Archimedean for this system. What we do yet, we have to though, or the system is imbalanced. It won't work. It's not mathematical. So where are we going? Well, we have two numbers now. And they're very peculiar numbers, you must admit. The one at the edge is imaginary. Well, that means that the reciprocal is imaginary too. So we have an imaginary number at the center and an imaginary number at the edge. Well, this sounds... Bear with me, because now something magical happens. You can picture the space with a center that has a number, and it's a special number, but it's related to another special number at the edge. Both of them are imaginary. You can't do anything in geometry with imaginary numbers. Although, if you study the complex number system, you'll see that there is a way to do that. And that's why complex numbers have replaced real numbers in all of physics. Physics no longer uses the real number system. It uses a higher order system of hybrid 2-component numbers, which you know are the complex numbers, an imaginary component and a real component. That's the only number system in use now. Dirac used it. Essentially, it's the basis of all physics, including Einsteinian mathematics, if it's formulated that way, which it is, on the Riemann sphere. So that is the furthest exploit that linear geometry has taken towards sphericity, is the Riemann complex number sphere. Extremely difficult to master. Well, that means it's wrong. It has to be simple to be true. You will learn that that is an absolute statement that should guide your progress in science absolutely. If it is not simple, then it is not understandable, right? To the degree that there's a fuzzy boundary there, because the perception of simplicity is somewhat subjective. Oh my God, our modern day physicists capitalize on that in order to prove that they're right about everything. So they're a little bit deceitful in that sense. We're not being deceitful, but we're also not being fanciful. But we haven't proved it yet. So let's get to the right nexus. We have a number at the edge that's lazy 8 over 1. That means, according to our hypothesis, that the center number is 1 over infinity. Think about that. How small is that? Pretty small. It's about the most you can say. It's as small as you can get and still be able to even think about it. That's why it's imaginary. Now we're going to substantiate that later when we get to hyperspheric space. But for now, I hope I'm not trying to confound you. But I do need to set this up so that you actually perceive the next step. You have these two numbers that are in relationship. What is their relationship? They're reciprocal. What does that mean? It means that you can multiply them together and you know what the result will be. That is the definition of reciprocity. The reciprocal principle in mathematics is based in multiplication and division. That's strictly a multiplicative space perception. That the two numbers, for instance, 2 over 1 and 1 over 2, multiply to 1. So these two imaginary numbers multiply to a real number. 1 is definitely a real number. Nobody has ever questioned that. A lot of questions have been raised about 0, particularly in my approach, but nobody ever has questioned the validity of the number 1 because it's the metric of linear space. The jump from 0 to 1 is the quantum jump of distance that establishes your linear spatial metric. It's the jump from 0 to 1. There is no number less than 1. If you say, yes, there is a very tiny number that you could say with Cantor, there's an infinite number of tiny numbers in the distance from 0 to 1. You can say that in linear space, spatial formulation, but it leads to a paradox called Zeno's paradox. We're going to solve that. So we now have 5 apples. The solution to Zeno's paradox and the other 4, these are highly covetable goals if it can be done, but so far it may sound like I'm just ranting. That's how a mad scientist sounds. If he can't prove himself clearly, he's going to sound nuts. All right, so we multiply them and get 1. Okay, so what? Well, here's so what. Spatially, you have the edge. It's so far out that it's imaginary. So you say, okay, an imaginary number over 1. Okay, now we have a 2-component number for an imaginary number. Great. But it represents the edge. The reciprocal represents the center. Well, that's the center of a sphere. And now you have the edge, and you've defined them. So now you know what the edge is. It's infinity over 1. Okay, whoop-de-doo. Well, that means that the center is 1 over infinity. Smaller than any number in this system. So small that it's imaginary. To the same proportion, you have a number at the edge that is so large that it's imaginary. But those are 2 reciprocal infinities. Well, those 2 reciprocal infinities multiply to 1. Well, where can that 1 be? It has to be between the center and the edge, right? Okay, let's draw it. Here's the center, and here's the edge. We're just going to say that this circle represents the imaginary edge, and the center represents an imaginary point. That's quite different from Euclid. Euclid said that the center is null. It's just nothing. We're not saying that. We're saying that the center is representable. It's not null. It's not nothing. But it is imaginary. This is why 0 has sometimes been conceived in certain mathematical extrapolations to be imaginary. That's why. But that actually doesn't solve the problem. This does, and here's how. If you're at the center and it's infinitely small, then any number is going to be away from it. So 1 is definitely off the center. It's off the center. But it doesn't reach the edge. The edge cannot be reached. To the same proportion, the center cannot be reached. It's imaginary. But 1 is not imaginary. It's not at the edge, and it's not at the center. That means that there's only one location for that 1. It has to be in between the center and the edge. Well, how far from the center is that 1? What is that 1? It's a sphere. It has to be a sphere because only spherically would the 1 be equidistant from the center. And 1 is not the center. So you have a 1 now that is a sphere. Now we have 3 numbers. 2 of them are imaginary, but the sphere is real. It's in the space. So it is a spatial number. All right, now we have a sphere which has an interior. So the sphere that we just drew, which has a value of 1, the whole thing is now a thing. You could think of it as being the alternative to the line. The line is obviously highly restrictive spatially compared with the sphere, which is pure spatiality. You come out from the center to a distance of 1. We call that the radius, but that's a linear concept because it's only one tiny line that you draw from the center to the surface. But the whole surface is 1. So when you draw from the center, from the imaginary center to the real edge of the sphere, that sphere has a value of 1. So inside the sphere are numbers less than 1. Those are real. 1 over 2, 1 over 4, 1 over 8 are inside the sphere. But the reciprocals are outside, going to the edge. So as the whole numbers, 2 over 1, 4 over 1, 8 over 1, we're using harmonic geometric numbers for now, because we don't want to count linearly, we just don't need to. So we're just saying 2, 4, 8, which is a binary sequence. It's still spatial, it's just not linear. We're getting to linearity because we have to recover it, or this would be incomputable. That's a bozo no-no. So we have to prove that there is linearity in the system. Well, we have a good start, because now we have a spherical 1. So the radius is not a single line. It's the radial line. It's the radial line. Think of it as just one line. The radius goes out, we say in all directions, but just say it's one direction. It's going out. And that's the spherical radius. What is that radius? That's actually computable. And that's how you get linearity back, is by computing a single line inside the sphere. What you will find to be the radius of that circle is the inverse of tau. That is 1 over 2 pi, is the radius of a sphere whose value is 1. Okay? So now we have a sphere that's a 1. That's actually a huge jump, but we're not done yet. We haven't fully developed the number system. This, by the way, is a number space. We just proved it. Because all the numbers are either inside the sphere or outside the sphere. Going outside the sphere, the numbers get bigger. Going inside, the same thing happens, but it's not a linear relationship between the outside and the inside. It's a spherical relationship. Can we use that mathematically? Yes, we can. Yes, we can. And it's fully linearizable because we can always get the radius of that sphere. So there's your linear embedded space. If you have this line, but you take just one linear line out of that, that's the derivative. That's the derivative of the radial radius. So the linear radius is directly mathematically derivable on a constant relationship called 2 pi, tau. All right, so you know that should make sense. I pray that that makes sense, because if it doesn't, this next step will not make much sense to you because you're already lost. If that's the case, rewind. I should have links to my previous series where you get much deeper explanation of the antipodal theorem and bootstrap theorem, which I'm recounting to you now. This is the proof step for our development of a new non-Euclidean number system, which is a two-component number system not based on add. It's based on multiply. But really, strictly speaking, it's the inverse of multiply. And I'll show you how those relate. Division and multiplication are equivalent to add and subtract on the line. Use multiply and divide in spherical space. And that is the true correlation of the two operators, which are add and multiply. Those are the two operators. Add and multiply. Add only works on the line. Now we're proving that multiply only works on the sphere. But that's not quite adequate, because we know that multiplication is closed on the line. Division is not. So it's really division that we're concentrating on to get the true geometric aspect of division. Well, that has been discovered. I discovered it. The true relation that takes the place of linear add is proportionality. That there are two numbers related on proportionality, not add and subtract to balance on zero. It's proportionality on unity. That's why lazy 8 over 1 is related to unity. 1 is unity. And the center number is simply the reciprocal. Don't think of it as division. Think of it as proportionality that's inverted. You have infinity related to unity with infinity, the vase or vase. So it's outside. It's on the pedestal of 1. So infinity over 1 is one number that's relating two numbers. Unity, which is inside the universe, and infinity, which is outside the computable, visible universe. That's extremely important in astronomy and cosmology, that whatever we conceive the universe to be must have an edge. It cannot be infinite. It cannot be infinite, but we know that infinity is there. So it is real. It's just imaginary. Well, that sounds like a mad scientist talking. But that is the right way to define infinity, that you begin by classifying infinity in terms of numbers. It's too big to be a number, but it certainly is related to numbers. It's whatever is the biggest number that in our minds must be imaginary. Well, that's the whole thing outside the visible universe. So the visible universe has to be delimited. Our James Webb Telescope is over the 10 billion year mark, and being able to look back in time as it's conceived to be under relativity. So that's a long ways. 10 billion light years is a long ways. It's getting close to what is perceived, at least mathematically, to be the mathematical limit, which would be the Big Bang, which is a singularity, and that closes the loop on that insanity. That is madness. To say that because the universe has no visible edge, therefore it must have a zero origin. That doesn't make any sense. Mathematically, geometrically, physically, it makes no sense no matter how you look at it. Well, that's considered to be an ultimate. Since it makes no sense, that must be the answer. That's how the Big Bang was derived. That's where your linear mathematics leads you, is to an insane notion of a Big Bang. So this is extremely profound. But now we have an edge to the universe geometrically. Because we've identified what is beyond the edge, it's at this number, that line separating infinity from 1 is the boundary between imaginarity and reality. So reality is under the spherical edge is 1. Okay, but it's not 1. We already found out where 1 is. It's that sphere that is harmonically equidistant from the center and the edge. It's not linearly equidistant. Then it would be halfway between the center and the edge. It's not halfway between the center and the edge. It's harmonically between the center and the edge. And that number is 1. Technically, because this is a two-component number space, it's 1 over 1. 1 over 1 is the number for the surface of a sphere, and that's an hour and 20 minutes. I've begun to sweat copiously, or perspire is the more polite term. So I'm going to cut this off right now, but I hope you've enjoyed the bootstrap theorem of the universe, that we now have a number space for real space, for the space that was discovered in physics to be universal space. We now have the mathematical system to address it spherically with a completely linearizable number system. Both numbers on that sphere are real numbers, as real as they get. It's 1 over 1. That's the foundational number. That is the Archimedean balance number of the universe. And to tantalize you, so you'll tune in again, that number 1 for the sphere is light speed. It's distance over time. So that sphere that represents the Archimedean balance of the universe is distance over, we say it's time. Albert Einstein got a linear solution for universal space that relates space to time. That is incorrect. It's superpositional though, so it is correct linearly, and that's why Einstein is my favorite genius. He got the linear solution for spherical space. What we want to do is integrate it so that it's the spherical solution to spherical space. He got the linear solution for spherical space. The way he did that was by linearizing time. Space is already linearized, but you know that those lines that are making the 3D system, which Einstein extended to 4D, that has a 0 at the center. That's wrong. We just proved it. The center of any system in the universe is not null. There is no 0. All numbers are 1 or greater. And now you have to realize that 1 over 2 is not less than 1. Geometrically, it's harmonically equivalent to 2. It's 2 going in. This is 2, 4, 8 going out. This is 2, 4, 8 going in. They're reciprocal. They're bound into one number. This number is the harmonic balance between inner space and outer space. That is actually a perpendicular relationship between space and energy. Energy is motion. Motion is the second component. The 1/1 represents space, proportion, perpendicular space. The radial line is one dimension, and the surface, which is the sphere, is a second dimension that is the dimension of energy. And that's where we're going to find time. Stay tuned. This is Anagalactic. Keep looking up. It's a full moon, but if you like the moon, which I certainly do, this is the best time to get out and look at the night sky. Most astronomers prefer the new moon. That's why it's holy in all the religions. The new moon is the true Sabbath, because that's when you get understanding from the source. The Creator, who wrote this universe for you. That's your importance. I hope you give that some thought. That's why science is pure religion. We'll be right back.